Hi everybody, here's a video on completing the square. Now completing the square is a process that is similar to the quadratic formula in that you can use it to solve any quadratic, even ones that can't be factored, but the process of it is a little bit different and it's related to geometry. So we already know if we're trying to solve a quadratic, you have to set it equal to 0 to find the x-intercepts, roots, or zeros. So if I look at this one here, this is a general quadratic here. Now, the first thing you should always try to do if you're going to solve, you should always try to factor first. And if I look at this here, there's no numbers that multiply to 14 and add to 7. So factoring wouldn't work. And in that case, you all are used to saying, oh, well, I'm going to use a quadratic formula. But there is another thing you can do. And instead of factoring, which goes into intercept form, you can also use a process called completing the square, which will put a quadratic into vertex form. So we have already practiced converting from form to form. You went from intercept form to standard, and you went from vertex to standard. You know how to go from standard to intercept. That's with factoring. You don't know how to go from standard to vertex, though. That's what we're going to learn today, going from a standard form quadratic to a vertex form. Completing the square is the process that allows you to do that. And again, it works for any quadratic, even ones that can't be factored, even ones with imaginary roots. So it really is just an alternative to the quadratic formula. And we are going to derive the quadratic formula using completing the square in class next week because there is a proof for the quadratic formula. So the whole idea behind completing the square is the geometry behind it, which I'm going to show you. And what you do when you complete the square is you just add a number c, like the number at the end here, ax squared plus bx plus c. You add a number c to your first two terms to make it a square. And what that means is you make it look like something one factor squared. And this relates directly to perfect square trinomials. Any of these here are examples of squares. You can even have a number in front if you want, like 4x minus 10 squared. So perfect square trinomials are going to come up a lot here because they're directly related to the process of completing the square. So I'm going to show you an algebra tile demo, and we're going to fill out a table with it. The important thing to realize with algebra tiles is jot this down so you don't remember, because you're going to have to be able to draw your own algebra tile diagrams as well. If you do algebra tiles, it's all about the geometry and area. So you're going to have a general x by x piece. We don't know what x is, but the sides are both x, so the area is x squared. Then you're going to have long pieces that have the same height as the square, but they're only going to have a unit width, so x by 1, which is x. And then you're going to have little pieces that have the same width as the long one, but they are perfect. They're squares as well, so the area is 1. So these are your three options for shapes. And what we're going to do is we're going to fill out this table here to figure out the process of completing the square. Now, you might remember it from 8th grade, I'm not sure, but this visual will definitely help you. So can you set up this table in your notes? Pause the video and set this up now so that whenever I show you the visual, you can just fill in as we go. So we have our expression here. We are going to be filling in our values c at the end. So this here will be our c value. And then we're going to write each as a perfect square. They're going to turn into perfect square trinomials. So pause the video quick. You should have the table copied down by now. So let's do this first one here. I'm going to have x squared plus 2x, and I want to know what number needs to go here to write it as a perfect square trinomial. So let's go to the visual here, and I have my x squared piece, and I have plus 2x. So remember, we're trying to complete a square. The name of the method makes perfect sense when you see it like this. So I'm going to take my 2x pieces and put one there and one there. And the number of little square pieces needed to complete our square is just one little 1 by 1 piece there. So we are going to fill in a 1 here. So I can put a 1 here now. That's how many tiles I needed to complete the square. And as I write it as a perfect square trinomial, this just becomes x plus 1 squared. You know this is a perfect square trinomial because the square root of c is 1. The square root of a is 1. You multiply them, giving you 1, and you double them, giving you 2. Don't forget that. We practiced perfect square trinomials already. So this factored is just x plus 1 all squared. So now let's do x squared plus 4x. We'll do a couple more, and then you'll see the pattern pretty easily. Instead of our 2x's Let's do our 4x's. And then in order to actually complete our square here, we need 4 little 1 by 1 tiles. So that's going to go here. And then we'll have a perfect square. And this factored would be x plus 2 squared. So now let's do x squared plus 6x. Now notice all my b's here are even, and there is a reason for that. Visually, I couldn't have an odd number for b. Like if I try to do x squared plus 5x, this isn't a square anymore, it's a rectangle. So we'll deal with those later and see what we would do. Okay, so now I have x squared plus 1, 2, 3, 4, 5, 6x. So to fill this thing in, I'm going to need 9 little 1 by 1 pieces. So I'm going to put 9 here. And this now is a perfect square trinomial. Factored, it becomes x plus 3 squared. Now one geometric insight I want to make sure you're seeing here. If I write it as a trinomial, like for example here, x squared plus 6x plus 9, that expression represents the area of this whole squared, but it represents it piece by piece. So the x squared is the blue, the 6x is the green, the 9 is the yellow. Whenever I write it as x plus 3 quantity squared, it's still the area, but I'm not writing the area as separate chunks. I'm writing it as one whole square. X plus 3 times x plus 3. So in your table, I want you to make note of that, and so at least you have the algebra tile written once or drawn once. Expression as a perfect square means you take and write the area as one whole side times one whole side. So for example, the x plus 3 squared, you have your x, 1, 1. So that's your x plus 3 times your x plus 3. So side squared. This here is taking your x squared, your 6x, which is these guys, and your 9, which is these guys. So you break up the area into the 3 separate pieces. So let's finish up the table quickly here. I have x squared plus 8x plus question mark. So let me fill that in. So I have my x squared plus my 8 green pieces. I'm going to need 4 by 4 is 16 1 by 1 pieces in order to visually and geometrically complete the square. This is a perfect square trinomial. Factored, it's x plus 4 squared. And one more, x squared plus 10x plus, you can probably guess what that one's going to be using the patterns. So I have my x squared plus my 10 greens plus 25 1 by 1 pieces. So I'm going to go here, and I needed 25 tiles. So that's a perfect square trinomial. This is written as a perfect square. So what I want you to do is, we call these our C value. Let's call all these numbers right here D values. What I want you to do is write down the following. So here's the box I want you to write down, and in the box I want you to answer. It's important that you can get this pattern on your own because that's how you're going to remember it. So I want you to figure out what is the pattern or the rule to go from here, these first 2 terms, to here. So what's a general rule you can write to get your C term, the number of 1 tiles needed? And then I want you to say, what is the rule or the pattern to write it as a perfect square? So what's the rule to get D from what we started with right here? So pause the video and think about that. From here to here, and from here to here. What do we do? So what you should have realized is that the rule to go from your first 2 terms to get the C term is you just take half of half of B and square. So for example, half of 8 is 4, squared is 16, half of 10 is 5, squared is 25. So you take half your B term and square it. And the pattern to write it as a perfect square to go from here to here is you just take your B term, the middle term, and you halve it. You write it in half. So half of B, and then you write it like that. So that is actually what you're going to have. That's the rule. So hopefully this helped you figure out that rule. So this isn't something you have to just memorize. It's something that you intuitively see. So let's practice completing the square with some basic things before we do a full-blown example. So in your notes, add in this rule here so that you don't forget it whenever you look back on this in a couple months. So to complete the square of x squared plus bs, you add half of b squared to it, just like this. So I want you to apply this here. I'll do one of them for you, and then you can finish them. So to complete the square, I need to figure out what this term should be. So to figure out what my c value should be, I take half of b squared. So that'd be -8 squared, which is 64. And then to write it as a perfect square, you just do half of b. So that would be -16/2, so -8. Go ahead and fill out the rest, and then we can check in class to make sure you did it okay. You can get fractions, just keep them as fractions. No decimals. No decimals ever when we complete the square. So finish filling this out, and then I'm going to go to the next slide. So pause the video. All right, so let's go ahead and actually complete the square so that you can see a whole process done out. Now, I said that this is an alternative to the quadratic formula. So I want to do the quadratic formula with this, and then right next to it, complete the square so that you can see some similarities and differences. Now, whenever you complete the square, you're going to get it in vertex form and solve it. It's like a 2-for-1 here. So let's go ahead and compare the two. So what I did here is I set out the quadratic formula. So if you need to finish copying what's up here, pause the video and do that. But I got the quadratic formula going here because this is just review. And we're going to make sure we get the same thing both ways. So I end up with the square root of 128 over 2. And I see a perfect square hiding in 128, and it is 64. So I'm going to take it out and make it 8 root 2 over 2. And all these guys can be divided by 2. So that's 6 plus or minus 4 root 2. So those are my two answers, 6 plus 4 root 2 and 6 minus 4 root 2. So let's go ahead and complete the square, and hopefully we get the same thing. So for completing the square, what I'm going to take is my original, and I'm going to look at this, and first of all, you can't factor this. It's not possible. So this number here is not part of my perfect square trinomial. Like if I keep it like this, it's not possible to factor it. So I'm going to, first of all, set it to 0 because I'm trying to solve it. And then because the 4 had nothing to do with this, I'm going to subtract 4 from each side and write it like that. Now what I can do is take the x squared, whoa, I forgot an x, get in there. What I can do is take my x squared minus 12x and complete the square. So I can write it as a perfect square trinomial. So this visual of writing the two bars is really helpful so you don't forget to do it to both sides. So I'm going to complete the square. So I'm going to take half of b and square it to get my c value. So that'd be -6 squared is 36. What you do to the one side, you need to do to the other. So now, hooray, we have a perfect square trinomial. So let's write it in factored form. So you would do half of b, which is -12 over 2, which is 6. That's how you factor it. And this becomes 32, -4 plus 36. So this right here is really close to vertex form. So what we're always going to do is take a little detour to vertex form, which would be x minus 6 squared. Move the 32 to the other side, and that would be my vertex form. And the nice thing about vertex form is I can get the vertex right away. I could graph it quickly if I wanted. And the actual vertex would be, let's see, this means move right 6. This means move down 32. So I have my vertex and my vertex form. So let's go ahead, and we're done with our detour. And let's keep solving. Remember, we're trying to solve for x here. So I'm going to square root and square root so that I can get rid of the squared. You can't get x alone as long as that square root, or as long as the squared is there. So now x is almost alone. I just have to add 6 to each side. And when I square root 32, there's actually two answers. There's positive and negative 32. So when I added 6 to each side, this is now 6 plus or minus root 32. Now 32 is 16 times 2, so I'll write it as 6 plus or minus 4 root 2, and yep, they're the same exact thing. So I'm going to do one more with you quick. All right, I have just enough time to do this. So here's my quadratic. I set it equal to 0 to solve it. This here is not going to be a good c because I can't factor it, so I'm going to move it to the other side. Now I need to figure out what c value should I put there to complete the square so that it's a perfect square trinomial. So half of b squared is 25 to each side. All right, so I got my perfect square trinomial. I wrote it as a perfect square. I did my detour to write it in vertex form. That means write 5 down 24. And here's the answer. And here's your U-try. See you in class.